Hey guys, we're going to learn a new skill today where we combine two things we've already mastered by now, hopefully. One of which is Ohm's law, which is a formula that tells us how circuits behave based on the voltage, resistance, and current in the circuit. And then we have filling in the gaps, which is a more recent skill we've picked up where we learn how to predict the answers to problems without doing much math at all. So combining the non-math with the math will allow us to solve more complicated problems that involve a little bit of both. So in this circuit, we have a light bulb, a cell, and then a bunch of measurement devices. There's also a switch that's being shown as open right now, right over here. But as we all know, when a switch is open in a circuit like this, that would actually break the circuit. So for all these circuits, we'll assume that the switch is actually closed. It's just that that would be a little bit harder to draw and represent because that would look like a straight line and that'd be easier to miss. So we're just making sure everybody knows there's a switch there. Anyways, the things that will determine the behavior of this circuit are the cell, which we have up top right here, and the bulb, which we have down here. Those are the things that are going to decide how the circuit will behave. These ammeters, left and right, and the voltmeter down below are just observers. They're just measurement tools. Down below, we have a table that tells us what those measurement tools are measuring, and only one of those three devices is kind of like reporting in on what they're seeing. So ammeter number 1 is reporting in that they see 0.75 amps of flow. Ammeter 2 reports in nothing, and voltmeter 1 reports in nothing. Now, it doesn't mean the circuit is broken, doesn't mean anything is zero, it just means that is currently an unknown. We don't know what's happening at that part of the circuit. So we could figure that out by filling in the gaps, but we actually don't have enough information to just do that right now. So in order to solve this problem, we have to first acknowledge that from now on, we're going to have to assume that a lot of bulbs have some resistance to them. And we'll have to use that resistance information in order to solve problems. So for this whole presentation, I'm going to assume that all bulbs have 20 ohms of resistance. And you'll have similar assumptions that you'll make about your homework assignments in the future. There may be some circuits where not all the bulbs are the same resistance, but you will still be able to use the skills that are taught in this video in order to solve them. So let's just get right into it. First thing is we're given a choice of calling this a series or parallel circuit. It is a series circuit, and you should be able to see that there's one continuous loop around the circuit that the electrons could flow through from here to here. And this voltmeter is kind of like its own little path, but electrons aren't going to flow through it because voltmeters have a large resistance. So first thing I would identify is that ammeter 2 will probably be showing a current of 0.75 amps. So why is that? Well, ammeter 1, which is reporting 0.75 amps, is in series with ammeter 2. And when two things are in series, they share current. They have the same current flowing through them. So whatever electron flow is going through ammeter 1 and through the battery and through that switch once it's closed will also flow through ammeter 2. So they will measure the same amount of current flow. And in fact, the bulb will have the same amount of current flow passing through it, but we don't have an ammeter right on the bulb detecting current flow, so we're not even asked about the current through the bulb. But we can assume that it is the current flow through A1 and A2. So then we're asked about voltmeter 1. And we're not told any information about the voltage given out by the cell, so we can't use that as information to figure out what voltmeter 1 would measure across the bulb. What we have to do, therefore, is use Ohm's law. So Ohm's law comes in a pretty little package like this, if you like using triangles, where it's V on top, I on the side, and R on the other side on the bottom. And what you can do is you can either use an equation or a triangle version of the formula like this to figure out how much voltage there will be across this bulb. Now, the bulb has some resistance to it for sure. In fact, we're going to assume that all bulbs have 20 ohms of resistance in this case today. It definitely has a current flow, an I, a current flowing through it, because we just discussed that the current in this circuit is the same everywhere. And it must have some amount of volts that are being used to power it from the cell. So we just don't know how much volts there is powering that light bulb. So we have to figure it out. So how do we solve for voltage? Well, according to this triangle, if I want to solve for voltage, I cover it up. And that cursor isn't covering it up very much. But if that was covered up really nicely, the only letters you'd still be able to see would be the I and the R. So if you want to solve for V, the calculation for that is V equals I times R. So V equals I times R. So what's the I? It's 0.75 amps of flow. And what's the R? It's the 20 ohms of resistance that we assume all these bulbs in today's lesson are going to have. So 0.75 times 20 gives us the voltage, which would be 15 volts. So now we've filled in the gaps. One of those gaps got filled in with our circuit knowledge. The other gap got filled in with our calculation from Ohm's law, where we calculated the voltage using current and resistance. So there's filling in the gaps with Ohm's law. Now let's just move on and do some more problems, and you'll get to see the patterns involved here, so you can do this pretty quickly in the future. So circuit 2, what kind of circuit is this? That is a series circuit because there is one loop that all the electrons move around, and that's that. Cool. So moving right along. So what are we told? We're told that voltmeter 1 is detecting, where is voltmeter 1? There it is detecting 3 volts of voltage. In a series circuit, we have a rule that says in series circuits, the voltage from the cell is divided up among the resistors or the light bulbs. So that means if voltmeter 1 is going to detect 3 volts, then voltmeter 2 will also detect 3 volts. So it'll be 3 and 3. So what does that mean? That means that the electrons that came out of here used 3 volts from that cell to push through that light bulb and 3 more volts to push through this light bulb. They had to put some effort into getting through both of the bulbs. So if it used 3 over here, and if they used 3 over here, then 3 plus 3 means they had a total of 6 volts before they reached those light bulbs. So they came out of the cell with 6 volts, they used up both of them, and then once they were done going through both the light bulbs, they probably had 0 volts left and went back to the battery to recharge. So a total of 6. So that means it's a 6-volt battery. Maybe that strategy will be useful in future circuits. So we've done the voltage part. Now what about the current? Well, we don't know anything about the current anywhere in this circuit, but like in the last problem, we don't necessarily need to know about the current as long as we know about the other 2 things in Ohm's law that can calculate current. So up here it says that I is in this part of the triangle where if you cover it up, you would have V over R as your operation you're going to do to solve for I. So I equals V over R. So let's try to find the current at position 2 because it's near these light bulbs. Well, the light bulbs have a voltage across them equal to 3 volts, and they each have a resistance of 20 ohms. That's what we said at the beginning of this presentation, is all the light bulbs for today would have 20 ohms of resistance. So if we know how much voltage is used on this bulb and we know how much resistance the bulb has, we should be able to use Ohm's law to calculate how much current there is flowing through that light bulb. So current, I, is going to be equal to V over R. So what's the voltage at resistor 2 or at light bulb 2? It's 3. So that's the voltage is 3. And what is the resistance at bulb 2? The resistance is 20 because all of them will have 20 ohms. So 3 times 20 is 60. So, mental math. So 3 divided by 20 is 0.15. 3 divided by 20, of course, because it's V over R, not V times R. Mr. Calamay is stupid. So there's the current flowing through A2. And A2 is right in between these 2 bulbs. Now that current that flows through A2 is going to flow through the bulbs, and then it's going to keep flowing, and it's going to flow through A1, ammeter 1, then through the cell, then through the switch, assuming the switch is closed, then it will flow through A3. So it's actually going to be the same current everywhere for the same reason we said that that would happen in the previous circuit. So A1 and A3 should both also be reporting 0.15 amps. Not 60. So 0.15 amps is the flow everywhere. It's the same flow that's being measured by multiple devices. Kind of like multiple people standing on the same road watching cars go around and around. It's the same thing that's flowing, but multiple devices are measuring it. So there's circuit 2. We'll start to pick up the pace a little bit here now with circuit 3. Circuit 3, what kind of circuit is that? Series or parallel? Definitely series because there's one loop for all the electrons to flow around. Let's start solving this problem. So A1, well, let's see. We know about A2. Ammeter number 2 is down here. It's detecting a flow of 0.9 amps. Because this is a series circuit, we can assume that the flow through A2 is also the flow through A1. So that means it'll be the same amount of flow, so 0.9 amps as well. What about the voltage? Well, anywhere here, you could say that all 3 of these light bulbs have a current flowing through them equal to 0.9 amps. So we know the I value flowing through either this bulb or that bulb or that bulb. We also know the resistance of all the bulbs. We know they're all 20 ohms for today. So R is something that we know. I is something that we know. So we can use those 2 to solve for V. So how do you solve for V? Well, according to Ohm's law, V equals I times R. So what is the current flowing through any of these bulbs? It's 0.9. What is the resistance of any of these bulbs? It's 20. So I times R, 0.9 times 20. That gives you an answer of 18 volts. Now, I had that first answering here for bulb number 2 or voltmeter number 2. And so there would be 18 volts there. Even if you just solved that for one light bulb, now you can apply that to the other ones and say, well, there probably is 18 volts given to that bulb and to the other ones. So you could assume that voltmeter 1 and 3 were also given their own 18 volts. Meaning if you wanted to know how powerful this cell is up here, even though we weren't asked about it this time, we might be asked about cells in the future, you could say that 18 plus 18 plus 18 gives you the total amount of volts that were distributed to that circuit. So it'd be 18 times 3 or 50... 54 volts. Mental math. So that leads us to circuit 4, which is a parallel circuit. So we're going to change our thinking a little bit here. What are we told? We're told that ammeter 1 up at the top is measuring a current flow through it of 0.6 amps. So 0.6 amps flows through A1. Then that would flow through the cell. Then that would flow through the switch. Then it would flow through A4. So really early on, we can actually assume that A4 is going to measure the same flow of 0.6. But then there's a break in the circuit where, well, not a break, but a junction where electrons can actually choose which path they want to take. They can either travel this way and go back to the cell, or they can travel this way and go back to the cell. So that flow of 0.6 that's going through A1 and A4 is going to break apart into two different amounts of flow. So ammeter 2 over here is going to measure some of the 0.6, a fraction of it. And then ammeter 3 down here is going to measure the remainder of it. So how will that current split? Well, because there's one bulb on this side and one bulb on the other, and we're assuming for today that each bulb is 20 ohms of resistance, then there's 20 ohms of resistance on this branch, 20 ohms of resistance on that branch, and that's the same amount of resistance. So there won't be any preference here from one path to the other. So electrons will equally choose the two paths. That means that each of the two branches will get 0.3 amps of flow. So there's a full 0.6 units of flow up top, but then it breaks apart into 3 and 3. And that 3 and 3 would rejoin later and become the full 6 going back into ammeter 1. So there our current answers are solved. How about voltage? So for voltage, we're not given any information. So again, we'll probably have to use Ohm's law here. So how do you calculate the voltage at, let's say, voltmeter 1? Well, voltmeter 1 is in a branch where there's a current flow equal to 0.3 because ammeter 2, which is in series with this bulb right here, it's in the same branch. That ammeter 2 says there's a flow going through that branch equal to 0.3 amps. So we know the current at that bulb. We know that the current I is equal to 0.3. What we also know is that the resistance of that bulb is, once again, 20. So we know the resistance, we know the current. So current times resistance, I times R, equals V. And so V, therefore, is I, which is the 0.3, times the R, which is 20. And so therefore, the voltage at voltmeter 1, at bulb 1, would be 6 volts. Now, here's where you could do that same problem down below for voltmeter 2 down here, or you could use your circuit rules knowledge to know that if one branch with one bulb was given a total of 6 volts, then the identical branch below would also get 6 volts. So both branches get 6 volts. So what does that mean? That means that any electron that came out of the cell had 6 volts to use, and it either used its 6 volts here on that bulb and then returned to the cell, or it brought its 6 volts down here, used it on this bulb, and then returned to the cell. Those are the two options. So there's 6 volts either way. If you measure this one up top, it's 6 volts. And if you measure this one down below, it's 6 volts because all the electrons use just their 6 volts at just one bulb, either or, one or the other. So that leads us to our first compound circuit of a few that we're going to look at. And a compound circuit is like a third option where there are aspects of series and parallel. So in this circuit, we can see that there's a current flow at ammeter 1 up top equal to 0.6. That's the same current that would flow through ammeter 4. So we can copy that number down and say there would also be 0.6 amps of flow through ammeter 4. And then we lose 0.4 amps of that flow out of the 0.6 going into ammeter 3, which is down below. So our total flow at the top of the circuit is 0.6 amps, but then that turns into 0.4 going down here. So where did the 0.2 go? Well, 0.6 minus 0.4, that's how I get the 0.2. Where did that flow go? It must have flowed into this branch over here. It must have flowed through A2. So 0.6 minus 0.4 is 0.2, and that 0.2 must have flowed through ammeter 2. So now all of our currents are figured out. What about voltage? Same thing we've been doing continuously here. We're just going to pick a bulb at random, and let's say voltmeter 3. Why not? The bulb on the bottom. We know enough information about that thing to figure out how much voltage is being used across it. So I'll just use the fact that the current at ammeter 3 is 0.4, and the resistance of that bulb is 20. So 20 times the 0.4, that gives you an answer of 8. And so there's 8 volts being used. So that means this entire branch is given 8 volts, and all of it is used on that little bulb right there. So that must mean that there's 8 volts provided by the cell. So if it's an 8-volt cell, and there's a branch with 2 bulbs on it, that 8 volts is going to have to be split up between the 2 bulbs. So this bulb will get 4 of the 8, and this bulb will get the other 4 of the 8 volts. So it'll be 4 and 4. So there's circuit 5. Circuit 6, here we go. Another compound circuit for sure. There's some aspects of series and some aspects of parallel. What are the parallel aspects? Well, here's one branch and here's another. What are the series aspects? Well, these 2 bulbs are in series with each other. One comes after the other. So this is a compound circuit because it has, both types in it, both series and parallel parts. Anyways, what are we given? We're given the voltage this time. Voltage at voltmeter 1 is detected as 12 volts. Voltage, again, is that push that's given by the battery to every electron. So if an electron comes out and has 12 volts and it goes through this branch, it'll use all 12 volts right there because there's just one bulb, and then it will go back. So if that's a 12 volt push being given by the cell, then we have to think if an electron went down here, how much voltage would get used at these bulbs? Well, if it's given 12 by the battery and there's 2 bulbs, then that means that the 12 is going to get split in half into 6 and 6. So that means that the 12 gets split into 6 and 6 volts. And so our answers for voltmeter 2 and for voltmeter 3 would both be 6. So now our voltage is all set. How about the current flow? Well, now we're going to go the opposite way we've been going before. We're going to actually calculate the current flow using the voltage. So we know the voltage at, let's say, voltmeter 1. We can pick any of the light bulbs to start out with. Voltmeter 1 has a voltage across it of 12 volts. And that 12 volts is going to get multiplied, or actually divided by the resistance of that bulb. So voltage is 12 at that bulb, the resistance is 20, so 12 divided by 20 should tell us the current flow through ammeter 2, because that's where that bulb is located. So ammeter 2 will measure 0.6, because that's 12 divided by 20. So 0.6 amps flows there. Now we could do the same calculation down below, or you could try to figure out what the difference is from that middle branch to the bottom branch. So what is the difference? The difference is there's one bulb up top, and there's 2 bulbs down below. So there's twice as much resistance down below. Because there's twice as much resistance, the electrons are going to be half as likely to go down there because it's twice as difficult to path. So if you had 0.6 amps of flow through this branch, and you're going to get half the amount of electrons going here because it's twice as challenging a path to take. Well, what's half of 0.6? Half of 0.6 is 0.3. So ammeter 3 will be detecting half the amount of flow that that other branch had. So it'll be 0.3 instead of 0.6. Now the question is, how do we figure out the current at A1 and A4? Well, when 0.3 from the bottom and 0.6 from the side meet up at this junction, they'll flow up together at A1 and form 0.9 amps when they add together. Then that flow is going to move through A4 and then split up again, infinitely looping around here. So A4 would also detect the 0.9 that happens before they split off into 0.6 and 0.3. That's circuit 6. Now on to a more challenging question. So is a series parallel or compound? Well, obviously it's compound. It's very complicated looking, and it is a little complicated, but it doesn't require any more skills than what we've been going over the last couple of circuits. So let's approach this one the same way we approach the others. What are we given? We're given that voltmeter 3 has a voltage across it of 4.5 volts. So where's voltmeter 3? There it is. So there's 4.5 volts there. Well, we know that when things are in series with each other, like this light bulb and the light bulb over here near voltmeter 2, when things are in series, they're forced to share their voltage with one another. They have to share their power. So that means that whatever voltage this cell is giving out to all the branches, an electron that chooses this path is going to use some of its volts here and some of its volts there. Now, remember that we've been assuming that all the light bulbs have the same voltage. Well, I'm going to just make the answer a little less predictable. And let's say on this slide in particular, all the bulbs will have 30 ohms of resistance, just to change it up a little bit. So all these light bulbs are 30 ohms. So we'll deal with that in a second. But first, how much voltage should I assume that this voltmeter over here is detecting, voltmeter 2? Well, if voltmeter 3 detects 4.5 volts, then that means that it's probably sharing that voltage that it gets on the branch with the other bulb. They're probably sharing their voltage. So that means that if the voltmeter 3 is detecting 4.5, then voltmeter 2 would also be using 4.5, and that makes the total 9. So an assumption I can make is that the cell must be giving out 9 volts because that middle branch got 9 volts, which it split up into 4.5 and 4.5. So now that we know how much voltage this cell has, we can assume that that's the voltage that every branch is going to get, because an electron that comes out of this 9 volt cell is going to have 9 volts to use. It'll either use its 9 volts at this one light bulb here, which means that guy will have all 9 volts to it and then return, or the electrons will come down to this bottom branch, or this middle branch rather, and use 4.5 of the 9 volts here, and then the other 4.5 there, so that still totals to 9, and then the electrons will return and charge back up. Or electrons will come down here to this bottom branch and use 3, 3, and 3, totaling 9 volts, to get through those light bulbs up to the top and back. So you'll notice in this diagram, it's shown a little more clearly than it has been before, that there is a different amount of brightness that you'll get out of bulbs when this happens. More volts will typically equal more brightness. So this guy up here that gets 9 volts, very bright. These guys down here that get 4.5, not as bright. These ones that get 3, pretty dim comparatively. So the voltage determines brightness to some extent, but it's really about current flow. So Let's now solve for this final bit here, the current. So we could choose anywhere in this circuit. And the first place that I would look is at A2. So I'm showing you the answer right away, and maybe we can see how we got this. Ammeter 2 is right next to bulb number 1, or voltmeter number 1, which is around that bulb right there. Voltmeter 1 gets 9 volts of voltage, and there is a assumed resistance of 30 ohms in that bulb. So if it's a 30 ohm bulb, that's R, that's the resistance. And if there's a current flowing through it that we need to solve for, then the only other thing we need is its voltage. So what is the voltage of that bulb? It's 9 volts. So the voltage V is equal to 9. The resistance R is equal to 30. So our calculation for current would be V over R. So the V is 9, the R is 30, so you do 9 over 30, and you get 0.3. So then we can compare that to the middle branch. So if the top branch had a flow of 0.3, then what about this middle branch that has twice the amount of bulbs? Well, twice the amount of bulbs means it's twice as difficult for electrons to travel through that path. So only half the amount are going to actually do that. So if the original amount of flow was 0.3, then half of that is the amount of flow we'll get going through here, because it's going to be half as likely that electrons will choose that path. So we take the number 0.3, we half it, and we get 0.15. So 0.15 will be the amount of flow that we get down here. What about the lower parts of the circuit? What about A4, for example? A4 is in the branch with these 3 bulbs. Now, it'd be really hard to compare 2 bulbs to 3 because we're going to get into some weird fractions if we do that. So let's go back and think about this first branch that had only 1 bulb, and let's compare that to the bottom branch. Well, the bottom branch has 3 times the amount of resistance and 3 times the amount of bulbs and difficulty for electrons to get through as that top branch had. So if this bottom path is 3 times as difficult to get through, it's going to have 1/3 the amount of current. So we cut this current into thirds. The 0.3 that flowed through here, we'll get 1/3 of that down here because it's 3 times as hard to move through that path. So 0.3 divided by 3 gives us 0.1. So that was the hard part right there. The easier part is now just combining all of these to figure out what the current should be up at the top at A5 and at A1. So all 3 of these currents, the 0.3 on the top, the 0.15 in the middle, and the 0.1 on the bottom, all 3 are going to eventually join back up after all those junctions and combine and flow through A5 all together. So that just means we have to add the numbers 0.3, 0.15, and 0.10, and the number you get, of course, is 0.55, and you will notice that I've put that also as the answer for ammeter 1. And so why is that? It's because A5 and A1 are in series with each other, so they share the same current. They have the current flowing through both of them. It's the same flow, just measured by 2 different devices. So that is filling in the gaps with Ohm's law. Good luck.